Hey there, Math Rockstars. This video is about using the rules of transformations, being able to explain how to change the parent function by changing what the equation looks like. And this is more of a put it all together kind of a video. If you have had some experience with transformations, this may be enough, but if this is the first time that you've looked at transformations and functions, you may want to do some of the activities in your packet first, some of the labs and explorations first. So this video is really more of putting it all together and kind of having all the rules written down in one place. But as always, you decide what's working best for you and then let me know how I can help. So the place to start with transformations is always with a parent function, and a parent function is the most basic of family function types. For example, if we start off with f of x equals x, that parent function's graph looks like just that simple line that goes right through the origin, has a slope of 1 and a y-intercept of 0. If I want to move that line someplace else in the graph, I have to transform the equation in some way. So for example, if I rewrote the function by adding 5 to x, that's going to take my graph and shift it up 5 units. 1, 2, 3, 4, 5. Still going to be the same slope, up 1 over 1. But now my graph has shifted 5 units up. Another kind of a graph transformation might be a reflection. So for example, if I started off with a very simple cubic function, so f of x equals x cubed, that parent function you might not be as familiar with, but you will be by the time we are done this summer. It looks like this. Sometimes I refer to that as the John Travolta function, and if you're not sure who John Travolta is, you should Google that. It's very 70s. And you can ask me when you see me next why that's called the John Travolta function, or you could try to figure it out yourself. If I want to move that cubic function someplace else in the coordinate plane, like say I wanted to flip it over the y-axis and slide it down, I would need to do something like this to its equation. I'd have to take whatever x's I was choosing and write the opposite, then cube them and subtract 2 from whatever it was that I got. And then my graph would look like this. It would have been flipped over the y-axis and shifted down 2 units. So this transformation looks like a shift down of 2 units and a reflection or a flip over the y-axis. And what I want you to be able to do is to look at a function and say, I think I know what the parent is, being able to recognize what the parent function is, that original, most simple, plain vanilla function, and then say, you know what, this function has been transformed in the following ways. It's been reflected over the x-axis. It has been stretched vertically. It has been translated up 5 units or to the left 2 units. Transformations move a function's graph around the coordinate plane. So the next thing we're going to do is to just create a little catalog of all those transformation rules. And once again, if this is the first time that you're looking at this, I would highly recommend that you do some of the lab activities. It's fine to look at this catalog and it's very useful, but you'll get a lot more out of actually moving some functions around yourself and just kind of playing with it. All right, so we're going to just write down what the function rule is, give you an example, and then draw a graph. So looking at the result. And we're going to do 2 kinds of transformations. One where we're going to be putting putting the transformation rule on the outside of the function, and another one where we're putting the transformation rule on the inside of the function. So here's an outside one, f of x, and then I'm going to add some number a to my function. So this is outside the function. An example of that would be if my parent function is the absolute value function, and I'm going to use that as my parent for all of our cataloging. If my absolute value function is the parent function, I could add something to that. So we'll add 4. It would look like this, the absolute value of x plus 4. And this transformation is going to always shift up. So if you're adding something to the function, it shifts the graph up. Shift up. And in this case, it's going to shift it up 4. So our graph is going to go up 1, 2, 3, 4 units, and then still look like our very familiar V. A similar thing will happen if I subtract something from, so I'm still outside my function, I'm subtracting something from my function. How about if we subtract 4 from the absolute function? This is going to result in a downward shift. So it's going to take the whole graph and slide it down, in this case, 4 units. So that's going to look like this. Still centered around the origin, but down 1, 2, 3, 4. And there's my graph. So these are all outside the function. I'm adding or subtracting something from the function itself. If I go inside the function to add or subtract, so in other words, I'm going inside and subtracting or adding something to the x, it looks like this in an example. I'm going inside the absolute value, and I'm going to add 4 this time. When I do that, when I go inside, I'm changing how this graph looks in terms of the x-axis. So when I was adding on the outside, I was shifting it up or down along the vertical axis, the y-axis, and now I'm going to go inside and I'm going to be shifting with respect to the x-axis, so along the x-axis to the left or to the right. So these are all inside the function, and these are going to be slightly counterintuitive. So if I add something on the inside of the function, I'm adding something to x, that transformation is going to shift the graph to the left. Adding shifts to the left. Really what's happening is the function is staying right where it is, and you're picking up the coordinate grid and moving it right. But what it looks like is that you've shifted it to the left. So over 1, 2, 3, 4 to the left, and there's my V. Same idea, you probably already are expecting this if I subtract on the inside. So my example would be taking x and subtracting 4 from it is going to shift my function to the right this time, opposite of what I might think. Over 1, 2, 3, 4 from the origin, and there's my familiar V. So adding and subtracting shifts the graph up and down or left and right, depending on whether you're adding or subtracting on the outside of the function or inside, adding or subtracting to the x. Let's take a look at what happens when we negate the function. So if once again, I'm on the outside, so outside. If I negate the function and make it a negative f of x, here's what my example looks like. Got a negative absolute value of x. That ends up being a reflection over the x-axis. So reflect over x-axis. It's going to look upside down. Same V, but now it's upside down. And think why that might be. I'm negating my y. So instead of it being positive, now it's going to be negative. And it ends up flipping over the x-axis. What happens if I negate the x? So now I'm going inside the function. So I'm negating the x this time. This is also going to be a reflection, but instead of reflecting over the x-axis, it's going to reflect over the y-axis. And in this case, because we've chosen the absolute value function, we'll come back here, notes, reflect over the y-axis. Sorry, my handwriting is getting so messy. Reflect over y-axis. Because it's an absolute value function, so let's just see what happens. So there it is to begin with. I would reflect that right leg over here to the left and the left leg over to the right. It doesn't look like anything has changed because the absolute value function is symmetric with respect to the y-axis. But if I had done something else, like shifted it to the left or to the right to begin with, then you would be able to see that reflection. But it really is getting reflected over the y-axis. A couple other things you can be doing to functions. You don't have to add or subtract or negate. You can also multiply by something, and when you multiply, you end up with a stretch or a compression, a stretch or a shrink. And once again, we can also talk about inside and outside functions with stretches and shrinks. We'll look at the outside first. So outside a function, if I multiply my function by some number a, and an example could be multiplying 5 times our absolute value function. What this does is to stretch or compress things vertically. So if it's going to be a vertical, it will be a vertical stretch if my a value is greater than 1. So in this case, it's greater than 1. It's going to be a stretch. And what that's going to look like is it's going to look like my v is closing up a little bit. So instead of being an open v, it's going to be more closed. If a is between 0 and 1, then it's going to be a vertical compression. Let me write that the other way around. So a vertical compression or a shrink compression if a is between 0 and 1. And you may be saying, well, what about negative? But remember, if you make it negative, then you're flipping things. So you're going to flip over the x or over the y. But if you just multiply by a fraction, like 1/2 of x, what happens when you're compressing the graph vertically? It will look like your v is opening up. But really what's happening is you're taking the vertical axis and you're squishing it. You're flattening it. Think of taking something between two planes and squishing them together. All that stuff kind of oozes out like two cookies, and you're going to put ice cream in the middle. You put ice cream sandwiched between two cookies, and then you press those cookies down towards each other. What happens is that the ice cream spreads out. And the same thing is happening when you multiply a function by a fraction, by some number between 0 and 1. It compresses the vertical axis, and it looks like it's opening up. So something very similar is going to happen when we multiply inside our function. So I'm multiplying my x by a. And what this would look like in our example is 5 times x is inside the absolute value bars. Now this is a horizontal stretch or shrink. And just like with the translations, the shifting left and right, it's going to be the opposite of what you might think. So if I'm multiplying by some number larger than 1, my horizontal change is going to be a horizontal compression. So horizontal compression. Oops. Compression. So that's if A is greater than 1. And then if A is less than 1 but bigger than 0. So the example would look like this. 1/2 times x, and take the absolute value of that. That's going to be a horizontal stretch. So the stretch happens when A is between 0 and 1. And they look just like the vertical stretches and compressions, which is very odd, but that's exactly what's happening here. A horizontal stretch or horizontal compression. So I'm going to stop here and encourage you to do some of those labs on your own to kind of explore this a little bit. If you weren't interested in the labs themselves, you could use your graphing calculator and try doing some stretching, shrinking, flipping with a variety of different functions and kind of prove to yourself that yes, this is really, really working. In the next video, we're going to look at what happens if we have multiple transformations. So is there an order of transformations? How does all that work? And over the summer, you're going to be using some algebra to be able to see the transformations hidden within functions, because sometimes it's not as clearly laid out as our great catalog. So see you in the next video.